Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will continue our discussion about the cumulative distribution function, also known as CDF. And we will also talk about the probability density function, or PDF. Let's begin. First, the idea will be showing you a couple of definitions and a theorem. Then we're going to use those definitions and apply that theorem to solve a particular exercise. Okay, so let me go to our lecture notes. Yeah, so that's the first definition I want to show you. That's definition 4.2 from our textbook, and what we're saying here is that a random variable will be continuous, right, if the CDF, remember that we used that notation, capital F, to refer to the CDF, the cumulative distribution function. Okay, so if the cumulative distribution function is continuous, then we're going to say that the random variable y is continuous. Now let me remind you that when we introduced the CDF, since you guys already are very comfortable, know a lot about discrete random variables, we found the CDF of a discrete random variable. And the CDF of a discrete random variable looks like a staircase. Remember? Well, that guy is discontinuous. But in this case, right, in this video, I'm going to show you an example of a random variable where it turns out that the CDF, that new function, capital F, happens to be continuous. Then we're going to say that the random variable is continuous. Okay? Okay. Now, there's another definition I want you to see. This is going to establish, it's going to give us a relationship between the CDF, capital F, the cumulative distribution function, and the PDF. And we're going to use lowercase f to refer to the PDF. And PDF is short for probability density function. Okay? And the relationship that we have between the CDF and the PDF is that if you have the CDF of the random variable y, all you have to do to obtain the PDF is just take the derivative with respect to the random variable, right? So in this case, just take the derivative of the CDF with respect to y. Okay? Make sense? Okay. Now, let me show you a theorem. We're not going to provide a proof of this result, but we're going to see that it holds for the variables that we're going to be dealing with. Okay? Anyway, remember that back then when we studied discrete random variables, we said that the distribution or probability mass function of a random variable y is just a list of possible outcomes along with the corresponding probabilities, right? Okay, and we also said that that probability distribution had to satisfy a couple of characteristics, right? The probabilities that we assigned had to be numbers between 0 and 1, and if you add them all up for all possible values of the random variable, the sum should be equal to 1, right? Okay, so what we have here in this theorem is something similar, but for continuous random variables, okay? So the first one is that if you have a legit PDF, remember that we're going to be using that term for lowercase f, the probability density function. So if you have a legit PDF, that function must be non-negative, meaning the graph of that guy should be on or above the horizontal axis, okay? So f at y should be greater or equal to 0, and that should hold for any number between -infinity and infinity. Okay, next property. So now, instead of a sum, we are going to have an integral for all values in the real line between -infinity and infinity. If you integrate the PDF, you should end up with a 1. Okay, so that theorem again is just an analogy of the properties that we had before for discrete random variables, okay, for probability mass functions. Okay, so now we are ready. Let me show you the exercise that I would like to solve with you. Okay, so we have a random variable y, and we are told that the probability density function lowercase f at y looks like this: c times y, as long as y lives between 0 and 2, including both 0 and 2, and it's going to be 0 elsewhere. Okay, now part A, we want to find the value of that constant c that makes that expression a legit PDF, a legit probability density function. Once we have that guy, we want to find the CDF, the cumulative distribution function, uppercase F. Part C, we would like to have a graphical representation of these two functions, the PDF and the CDF. Part D, once we have the CDF, we would like to use it to find that probability, the probability that the random variable y is between 1 and 2, including 1 and 2. And finally, we would like to find the same probability, but using geometry, okay, and the PDF. Make sense? Okay, so here we go. Let's try and do that. Okay, so first, remember that just from theorem 4.2, right? We have it here, slide 15. If we want that expression to be a legit PDF, we need the integral from -infinity to infinity to be equal to 1. Okay? So here we go. Let's begin. So exercise 4.11, part A, right? We want to find that constant that makes that expression be a legit PDF. Okay? Okay. So, as I was saying, by property 2, we would like to have this. Okay? So, by property 2 from theorem 4.2, we want the integral between negative infinity to infinity of f of y with respect to y. We want that integral to be equal to 1. Guys agree? Okay. So now let's be super specific. Later, once we have more experience dealing with these guys, well, we're going to be able to you know, cut a few corners, if you will. We're going to be able to just implicitly say, oh, I know where I should be paying more attention. Okay? So, but first, note that we have that lowercase f, right? The candidate for a PDF up to that constant that we have to determine is given by this 0 elsewhere. And if you're dealing with a value between 0 and 2, you have c times y. Okay, so elsewhere. So meaning that what we want here, if we're going to be super careful, and that's what we're going to be doing here, we're going to be very specific. What we want is the integral from negative infinity to 0, right? And in that case, the expression of lowercase f is 0, right? Plus, if y lives between 0 and 2, then we are going to have a different expression for lowercase f. So it's going to be between 0 and 2. We have c times times y, and then for this one, between 2 and infinity, we have 0 again, right? Make sense? So we broke down that integral into 3 integrals for 3 different regions: between negative infinity and 0, between 0 and 2, and between 2 and infinity. Make sense? Clearly, the first integral and the last integral are 0, right? So the only one that matters in this case is the second integral, the one in the middle, right? So that's what we want. Now, note that by the linearity of integrals, right, we can pull that constant out, right? So that's what we're going to be doing next. So let's pull that guy out. And then if we divide it by c on both sides, we would have the following relationship, that 1 over c happens to be the integral of y dy, right, from 0 to 2. So if we find the value of that integral, we're going to have the reciprocal of the constant that we're looking for. Okay? So let's find it. This one is really easy, right? We know that the integral of y dy will be just y squared divided by 2, and then we have to evaluate that at 2 and 0, right? You guys agree? And that will be equal to 1 over c, right? Again, the integral of y dy with respect I'm sorry, the integral of y with respect to y is going to be just y squared divided by 2. And then what we have to do is evaluate at 2 minus the evaluation at 0. So let me do that here. And that is going to be equal to the reciprocal of the constant that we are looking for, right? So that's just 4 divided by 2, that happens to be 2, equals 1 over c. Make sense? Therefore, c must be 1/2. You guys agree? Therefore, c equals 1/2. Make sense? So we have part A. Okay, let's go back to our problem. Now what we want to do is finding uppercase f at y, meaning the cumulative distribution function, CDF. Let's try and find that guy, part B. So just like the PDF is defined between -infinity and infinity, we have to find the CDF for any real value. Okay, so just like before, let's take a look at the support, we call it, of the PDF, meaning the values, right, of the random variable y. So we have that if y is less than 0, the PDF is 0, right? Okay, so and before we do that, also let me remind you about something, right? Recall that uppercase F evaluated at y equals the probability that the random variable is less than or equal to that particular value lowercase y, right? Okay, so anyway, going back to what I was saying, just like we broke down this integral into 3 parts, well, we're going to do something similar to find the CDF. Okay, so if y happens to be in this interval between -infinity and 0, okay, without including 0, we have this. Okay, so case 1. Case 1. If y is less than 0, okay, then what we want is, let's use this, we want the probability that the random variable y is less than or equal to some number, right? Which is less than 0. But then we use this. The definition of the PDF, right? Hey, in that case, we know it's the integral from negative infinity to y, right, of the PDF f at t dt, right? That's the way that you would find the probability of being less than or equal to y. Before, when we had a discrete random variable, it would be the sum up to that point, right? In this case, we no longer have a sum. We have the integral, right, of all values to the left of this guy. Okay, so this guy is the upper limit of that integral, right? And then here we have the expression of the PDF. But we know that if that y lives in that particular interval, if y is less than 0, in that case the expression that we need for the PDF is just a 0, which means that, guess what? 0. Okay, so the CDF for any number that is negative is going to be 0. Okay, here we go. Case number 2. How about now we have a number that lives between 0 and we have greater or equal and less than 2. So we have that y is a number that is greater or equal to 0 and less than 2. Okay, now by the way, why am I doing it like this? Why am I doing this 0 greater or equal to y? Remember when we talked about the properties of a legit CDF, we mentioned that among them you have that the CDF must be right continuous. Okay, so anyway, that's why I'm defining these intervals like that. Okay, so here we go. Let's do something similar to what we did before. Hey, y is just some number, for instance 1. 1 is a number that is between 0 and 2, right? So if we want f at 1, we want the probability that the random variable is less than or equal to 1. And that would be the integral from, and here's the part where this is going to be useful. Note that this is just by definition, right? Up to this point. Hey, you want f evaluated at some number, uppercase f evaluated at some number, then what you want is the probability that the random variable is less than or equal to that particular number, right? And since we have a continuous random variable, it's not going to be the sum, it's going to be the integral from negative infinity up to that point of your PDF, right? But if you are here between negative infinity and 0, you want the integral of 0 dt, right? Now, if and that's what we know, this guy is between 0 and 2, in that case, right, it's from 0 up to y, But now the expression for the PDF changes, right? It's going to be c times y. And what we said is that c equals 1/2. Remember, we found that guy. So it's just y divided by 2. Oh, t, right? We have to change variables here, otherwise our mathematician friends would get mad at us, right? Oops, let me change this guy. I don't want that plus there. There, okay. Make sense? Yeah? So, same idea as before, and that's why this guy, uppercase F, gets that name. It's the cumulative distribution function. It's the probability up to that point. Okay? Okay. Let me go to the next line. So this one is 0, not a problem. Then this is 1/2. I could factor it out, right? So that's what I'm going to be doing. So that's a 1/2. This guy is just t, right? And then what we have is the integral with respect to t of t, right, is t squared divided by 2. You agree? Right? So, but then I have to evaluate at y minus the evaluation at 0, right? So when we do that, right, it's going to be t squared divided by 2, right, times 1/2. That's going to be just t squared divided by 4, right? Evaluate it here and here. So let me write that down, okay? So it's going to be y squared divided by 4, right? Because we had t squared divided by 2 times 1/2, right? Then we evaluate at y, and then minus, and just to be super explicit, 0 square divided by 4. So in the end, this is just y squared divided by 4. Okay? Make sense? So that would be f at y, and we might as well put it in the next line. F at y. If y lives between 0 and 2, it's going to be y squared divided by 4. Make sense? We're almost there. Now we need the other case, right? What happens when you're between 2 and infinity, including 2? So case number 3, let me write it down like this, okay? Case number 3, between 2, including 2, and infinity. Well, again, we use the definition of the CDF. It's this, right? It's the probability that a random variable y is less than or equal to y. Since we have a continuous random variable, that is going to be the integral from negative infinity to y of the PDF, the probability mass function. Okay, so we know that now, instead of having two integrals, we are going to have 3, right? It's going to be the integral from negative infinity to 0, or 0 dt, right? The integral from 0 to 2 of t divided by 2 dt, and then we would have a third integral that I'm going to write down in just a sec, plus, and this is a 2, right? And what we're going to have is now the integral from 2 to infinity of f at t, right? But it turns out that the PDF evaluated in that interval is just 0, right? It's 0 outside the interval 0, 2, right? So the only one that matters is this guy. But note something, that when y is exactly equal to 2, you have this integral. If you do that integral, the one in the middle, you're going to end up with t squared divided by 4, evaluated at 2 minus the evaluation at 0. So that's going to be just y squared divided by 4, but when this guy is 2, that's 2 squared, 4 divided by 4. That's just 1, right? Okay, so that's what we have. That uppercase F at y, that case, if y is 2 or greater than 2, is just going to be 1. Make sense? Are we good? Not that hard, right? We're just using those definitions that we know. Okay, part C. I already prepared those graphs for you, but we're going to use what we have been doing together from parts A and B, right? So for from part A, what we have is that the PDF, right, is 0 outside the interval 0, 2, but now what we know is that the PDF, the probability density function, is y divided by 2, right? So that's a line, right? That's a line with a slope of 1/2 and y-intercept of 0, right? So let me see, I think I have a nice graphical representation of that here in our lecture notes. Okay, so it's 0 outside the interval 0 to 2, and it's linear, right? Make sense? Okay, so can you see, right, that that function satisfies the properties of a legit PDF? It's a curve, a function that lives on or above the horizontal axis, right? That's property 1, right? And the other one, if you take the integral with respect to that random variable, in this case y, from negative infinity to infinity, it's going to be 1. And in this case, once we have the graph, we go, oh, nice, this is a triangle. The area underneath that density is just the area of that triangle, right? Base 2, height 1, 2 times 1, 2, divided by 2, because that's a formula for the area of a triangle, then that's 1. So good. Okay, now that's the graphical representation of the PDF, probability density function. Let's talk about the graphical representation of the CDF, the cumulative distribution function, uppercase F. So what we said is, if y is less than 0, then the CDF will be 0, right? And let me go back to this. Oh, makes sense. If this is just a flat line, the integral underneath that flat line, 0, right? Because, I mean, you can see that, right? The area there, 0. Okay. Now, if y lives between 0 and 2, what we said is this guy will be y squared divided by 4, right? And going back to this, it would be, hey, for instance, if you took the area, if you found the area up to 1, this guy, right, that would be the integral underneath that triangle up to 1, and that would be uppercase F at 1. But you do that for all the numbers between 0 and 2, okay? And that is going to be what we have here, y squared divided by 4. That's going to give you the area underneath that triangle for any number between 0 and 2. And once you're beyond 2, then you have all the area that you could have, right? Because then what's the probability that the random variable y is less than or equal to 3? Then you go, that's going to happen for sure, because the random variable could be anything between 0 and 2, so it's going to be less than 3 for sure, right? Anyway, let me show you that graphical representation of our CDF. See, 0 between negative infinity and 0, then we have that curve, y squared divided by 4, and then we have 1. Make sense? Okay, so that's part C. That was nice, right? Having a graphical representation. Now let's go back to part D, the kind of problem that we wanted to solve. We wanted to use our CDF to find a particular probability. Okay, for part D, we wanted to use the CDF to find this probability here. Okay, so let's use it. Part part D. C, done, right? Those graphs, done. Part D, what we want is the probability that y is between 1 and 2, right? Let me just double check. Yeah, between 1 and 2. Less than or equal to less than or equal to, okay, so that's a probability that we want, that y is between 1 and 2, including both 1 and 2. Now, in this case, what I want you to see is that what we could do, this would be, one way of finding it would be the integral from 1 to 2 of the PDF. Okay, you can try and do that and check that you will end up with the same answer that I'm going to show you using a different approach. So it could be the integral from 1 to 2 of the PDF. Okay, that's one way. So one way using your integral. Okay? The other one, another way. I am a lazy guy, and we have already worked really hard to find the expression of the CDF from negative infinity to infinity. Okay, so let me show you something. The probability of that event, the probability that y is between 1 and 2, we could rewrite that like this. The probability that y is less than or equal to 2 minus the probability that y is less, strictly less than 2. You guys agree that if I do that, that would define the interval that I am interested in? Can you see that? Oh, and this should be 1, right? Not 2. Make sense? You guys agree? Now, something that I also want you to see is that, remember that in the case of a discrete random variable, it is not the same saying less than or equal to 2 than less than 2, strictly, right? Including 1 point could make a difference, potentially. Well, it turns out that in the case of a continuous random variable, one single point doesn't make a difference. Let me try and argue why that is the case. So, if you want just the probability of hitting 1 point, one way of thinking about it would be, for instance, what's the probability that y is exactly equal to 1? Then you would go, oh, it would be the probability that y is between 1 and 1. So it would be the integral from 1 to 1 of the PDF. But then when you do that, you realize, oh, then the probability of y being equal to 1 is 0, right? Because it would be like the area of a rectangle with a base of length 0, right? So no area there. So anyway, let me just say that since y is a continuous random variable, this is the same as this. One point is not going to make a difference. Okay? Because y is continuous. And again, it's just because, you know, when the upper limit and the lower limit of that integral, when they are the same, then you have no area. Okay? Okay. So, but now note something interesting. The probability that y is less than or equal to 2, that is precisely uppercase F evaluated at 2. You agree? And this guy here, the probability that y is less than or equal to 1, that is precisely uppercase F evaluated at 1. Right? And then since you found the expression of the CDF for any number between negative infinity and infinity, all we have to do is evaluate that function at 2 and at 1. So if I have that y is 2, I just go, oh, if it's 2, then, oh, f at 2 is going to be 1, right? So that's the first one. 1 minus, and now I need f at 1. And then we go, if y, oh, y is 1, that's between 0 and 2. In that case, one I want to use is this, y squared divided by 4. So 1 squared divided by 4. Minus 1 squared divided by 4. So that's just 1/4, right? So it's going to be just 1 minus 1/4, so that's just 3/4 in the end, right? And that's it. We are done, right? So that's why these CDFs could be very useful, because if you find them in general, then if you want to find probabilities for particular events like these, you could rewrite those events in terms of evaluations for the CDF, right? So that's why those guys are useful, very useful for continuous random variables. Okay, finally, just let me show you something. Let's very quickly do part A using R. Remember that in part A what we did was finding the constant that made that expression the expression of a legit PDF. So let's try and see how you could find that constant using R. So let me launch R. If I remember correctly, right, we found that the constant was 1/2, right? We have it here, so we could check. So what we said is, for part A, did this. Let's find that integral, and then our constant is going to be if we find this integral, what we have is the reciprocal of the constant that we want, right? Okay, so what we saw is that the value of that integral, the integral from 0 to 2 of y dy, happens to be 2, right? Okay, and then what we said is, okay, that's the reciprocal of what I want, c must be 1/2. Okay, so let's try and find, using R, that integral. Okay, the integral from 0 to 2 of y dy. Here we go. First, what we have to do is, let me just say that we are redoing part A, right? And remember that when you use those hashtags, what you're telling R is, I'm just, commenting my code. So R is going to ignore what you do there. Okay, so anyway, first what we have to do is define a function, and we're going to define it like this, f. And you could do an assignment in R using an arrow like this, or using an equals. Okay, so let me use an arrow in this case. I'm going to define a function, and I'm going to save that object as f. Okay, so the function f that I'm defining has as a variable y, and the expression is just y, and that's because I want this guy, right? The integral of y. Okay, now this is our function f, which is just, in this case, y. Let's integrate that function f. The lower limit is 0. The upper limit is 2. See what happens. The integral from 0 to 2 of y dy is 2. Okay, nice. Well, let's summarize. What we did here today together is we talked about a couple of definitions and a theorem. Those definitions had to do with first, the way that you're going to be able to tell whether or not you're dealing with a continuous random variable. And if your CDF is continuous, that means that you are dealing with a continuous random variable. So for instance, in this case, right, remember our graph. Guess what? CDF is continuous, so the random variable must be continuous. Okay? The other definition that we talked about is one that establishes a relationship between the CDF, the cumulative distribution function, and the PDF. Okay? So if you take the derivative of the CDF, you will get the PDF. Okay? Okay. And finally, we talked about a theorem that tells you, that gives you the characteristics that a function, probability density function, must satisfy in order to be a legit PDF. And those are: f must be a non-negative function, something that lives on or above the horizontal axis, right? And the integral from negative infinity to infinity of that guy, meaning the area under the curve, from negative infinity to infinity, must be 1. Okay? And that's the case in this particular example, and it's easy to check using just geometry, because it's the area of a triangle. Okay? But we can use integrals as well. And we will need to use integrals when we have more complicated PDFs, and we will have them in the near future. Okay, so that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.